All right, so good news is we're going to talk. The last thing we're going to talk about is I'm not going to do any more graphing. So that's probably good news for you guys. You will have to do this for your homework and possibly on your third exam. I won't be writing that one, so I can't actually say what's going to be on there. But the last thing we're going to talk about with graphing is symmetry. But we're not going to actually do any graphing with this. So we have 3 rules of symmetry. So the first one is if you have a function, so if the polar equation is unchanged by replacing theta with negative theta, the curve is symmetric about the polar axis. And the polar axis is the axis I measure angle from. This would correspond to the, if you're thinking about this in terms of x, y, it would be the x-axis. So an example of that is something that's going to look like this. So that's kind of symmetric. It's supposed to be totally symmetric, but so the point is, this has a coordinate r theta. This has the coordinate negative r theta. So this thing has symmetry about the polar axis, and this one here is the polar axis. Again, you can think about it in terms of, it's the angle, it's the axis you measure angle from. Sorry, that's not negative r theta, that's r negative theta there. And this curve has the same, value of r for both of those. Okay, so that's going to be that example. That one, this is just help, if you were drawing, something like type part A, you could draw half the curve and then reflect it about the polar axis. Okay, so let's do B. So if the equation is unchanged when r is replaced by negative r, or when theta is replaced by theta plus pi, the curve is symmetric about the pole. And what this means is rotate it 180 degrees and you have the same shape. So what that's going to look like is this. Let me get this right. And then if I do, yeah. So trying to draw this is not fun. So the idea is, if I look at these 2 points, so this is negative r theta and r theta. So what this means is, so if you do either of these replacement rules, you can draw half the curve and then just reflect it across, you know, the other half that you haven't drawn, to figure out what it looks like there. Part C. This one's a little easier to imagine. If the equation is unchanged when theta is replaced by pi minus theta. So these are like our even and odd rules. They're just these weird, they're these weird rules that let us, you know, figure out some sort of symmetry. The curve is symmetric. About theta is equal to pi over 2. So this would be, you know, what you would think of about as, you know, the negative y-axis, the positive y and negative y-axis. So an example of that is going to be something that looks like this. So let's do supposed to be symmetric again, but if you reflect across, let me use a different color. If you reflect across this line, you get the same thing as the idea. So that's going to be the last thing I talk about, you know, with this graphing stuff. This symmetry stuff just really helps you with, you know, this will help you identify curves. And it'll let you do the homework a little easier, maybe. Let me. So I say the curve is symmetric about the pole here. That's going to be the origin. That's what that means. So let me throw that in there just so I'm not confusing you. So this is going to be, you know, it's going to be the symmetry about the line y equals x. You can think about in terms of, you know, Cartesian coordinates. We have that kind of symmetry. So yeah, so with the odd functions, those are symmetric about the origin. That's what that kind of symmetry is. Part B, symmetry about the origin, like odd functions. Okay. Let's talk about something a little easier to, you know, think about. Hopefully, let's do tangents to polar curves. So we're going to get back into calculus. So this will be the last thing we talk about. I'm going to define how to determine the slope of the tangent line. We'll do an example. That'll be it for this section and again for this week because of your exam on Thursday. But let's go ahead and do this. So let's suppose we have r is equal to f of theta. And then we can think about this, what we can do if we have this relation. We can think about, you know, our relations here. R is equal to x is equal to r cosine theta. Y is equal to r sine theta. We can think about these being parametric equations now. So what I'm going to do is I'm going to replace that r with f of theta cosine theta, and y is equal to f of theta sine theta. Now I have x as, you know, just a function of theta, y is equal to a function of theta. This is just a parametric equation that we had from earlier sections. And so we can write down, you know, the derivative dy dx. It's going to be dy d theta divided by dx d theta. So what this is going to be is so the book writes it kind of weird. Yeah, I'll go ahead and write it that way. So what they're gonna do is they're gonna take the derivative of these two equations, and I'll stick with it. And you have to use, you know, product rule there. So dy d theta is going to be dr d theta times sine theta plus r times cosine theta. So product rule there for the derivative. Same thing on bottom. So x is equal to r cosine theta, so we're going to get dr d theta cosine theta minus r sine theta for the derivative. And again, you're going to have r as, you're going to have r as a function of theta. And now all of our previous rules apply here. Sorry, it's getting late here, so words aren't coming as easily. So all of our regular rules are going to apply. So to find horizontal tangents, we look where dy d theta is equal to 0 and dx d theta is not 0. And same thing for vertical tangents. We're going to have dx d theta is equal to 0 and dy d theta is not 0. So last thing I want to say is sorry, that's a 0, not a 6. So last thing I want to say is if we are looking for a tangent at the origin, we'll have r is equal to 0. And then the equations will actually simplify a little bit. So what we'll have then, if r is equal to 0, is we'll have, so if r is equal to 0, I'm going to plug, r equals 0 into this equation. I can't just set the derivative equal to 0, because just because the function value is 0 doesn't mean its derivative is 0. So what I'm going to get is dr d theta sine theta divided by dr d theta cosine theta is equal to dy dx. So that's going to tell me dy dx is equal to tan theta if dr d theta is non-zero. So this is just a special case. What you really want to remember is either have this memorized. Well, you guys have your books during the exam, so it doesn't matter. But you want to know where that comes from. So I'm going to stop the video here. I'm going to I'm going to do an example where we find the tangent to a polar curve, and that'll be my last example for this section.